Hello and welcome back to another chapter of our Calculus 2 course entitled Improper Integrals. As I certainly hope you may remember, the fundamental theorem of calculus states that the integral from a to b of f of x dx is actually big F of b minus big F of a, where big F of x is an antiderivative of f of x. We have used this profusely. You may also recollect that there was a preliminary condition to this result. F of x has to be continuous on the closed interval AB, where both a and b are real numbers. So what happens if this condition is actually not respected? For example, could we evaluate the integral from 1 to infinity of x e to the x dx? And the answer is no, because the upper bound is infinity. It's not a real number. It's not a number from a to b. Could we evaluate this other guy here, 1 to 2, x over x minus 2? And the answer is still no, because if I replace this bound 2 inside the function called the integrand, I'm going to get 2 over 0, which is undefined, and if the function is undefined at that point, it is not continuous. That means that I can't apply FTC part 2. So in the previous couple of examples that I've shown, FTC cannot be applied. These are actually called improper integrals and require a special treatment if we're going to be able to evaluate them. So in this section, we'll actually consider two cases of this. We'll consider case 1, where you have either infinity at the upper or lower bound, and we're going to consider case 2 where no infinity, but either f of a or f of b makes the integrand undefined. Let's take a look at some examples here and decide if they are improper or not. What about the first one? Minus 3 to minus 1, is that improper? The answer is yes, because the lower bound minus 3 makes the integrand undefined. If you replace minus 3 inside the function, you'll get minus 2 over 0, which is undefined. Here, the second one, 4 to infinity of x ln x dx, this is also improper. This time because the upper bound is infinity, not a real number. In the third example, I have a denominator x minus 7, so I know that when x is 7, that's going to be undefined, but 7 is not included in the interval 2, 5. So the function is not discontinuous on the interval 2, 5. We can integrate this one with standard means. Now, would it still be possible to evaluate improper integrals if we deal with the problematic bound in a specific way? Certainly. Let's see how case 1 pans out. If we actually replace the bad bound plus or minus infinity by, say, w, and we apply a limit as w approaches this plus or minus infinity bound, then we get the following expression. We replace infinity with w, and we let w go to infinity. In the case 2 situation, well, we have a bad bound of a here, so we replace the bad bound a with w, and we let w approach a from the right. That, of course, is if f of a is not defined. If f of b is not defined, then we replace the b with w, and then we take the limit as w approaches b from the left side. Let's consider a couple of examples and see how we can apply this solving method. Example 1, the integral from 1 to infinity of 1 over x squared dx. Clearly, a case 1, because the upper bound is infinity. So we replace infinity with w, and we take a limit as w goes to infinity. The integral of 1 over x squared is easy. It's x to the minus 2, which is x to the minus 2 plus 1 over minus 2 plus 1. Simplify, you get minus 1 over x. And then you can apply FTC part 2. Bring in the w, bring in the 1, minus 1 will give you plus 1. Now you can replace w by infinity. Minus 1 over infinity is 0, and 0 plus 1 is 1. When the answer to an improper integral is actually, like the previous one in example 1, a real number, we say that the integral converges. Otherwise, we'll have to say that it diverges if it turns out to be plus or minus infinity. Here's another example. This time, let's consider the integral from minus infinity to 4 of x e to the x squared dx. That's improper. Case 1 again, lower bound, minus infinity. So vamos. Replace the minus w, the minus infinity, with w, and let w go to minus infinity. This time, I can't do this integral directly. I will need a substitution. So I go aside, and I say u is equal to x squared. Du is 2x dx. I isolate my dx. I replace. It's an easy integral. The x's cancel out. I get the integral of e to the u du, which is, of course, e to the u. And since u is x squared, that's the answer to the integral. We're now ready to bring back the limit and the bounds. So now we have the limit as w goes to negative infinity of the answer to the integral we found between 4 and w. So put in the upper bound 4, put in the lower bound w, take the limit, that's 1/2 e to the 16, minus, here's a tricky one, minus 1/2 e to the minus infinity squared, which will be positive infinity. And e to the positive infinity, well, that's infinity. So we end up with the number minus infinity, we will get minus infinity. In that case, this integral diverges. Another example, this time of case 2. Integral from minus 1 to 7 of 1 over the cube root of x plus 1. Clearly, minus 1 is the bad bound because it makes the denominator 0. So we'll replace it once again with w. Let w approach minus 1 from the right side, of course. And here again, substitution is needed. So u is x plus 1, du is dx. And we integrate 1 over u to the 1/3, bring it up. U to the minus 1/3 plus 1 plus 1, 3/2 u to the 2/3, that's 3/2 x plus 1 to the 2 over 3. Again, we forego the plus c because this is actually a definite integral coming up with its limit. So what do we have here? We have the limit as w approaches negative 1 from the right of the answer to the integral we found between 7 and w. Plug in the 7 as your upper bound, plug in w as your lower bound, and replace w with negative 1. Here, this is just h to some power, and this is actually minus 1 plus 1 to some power. Minus 1 plus 1 is 0. 0 to the 2/3 is 0. The only thing that I have left is this guy, which turns out to be 6. So this integral clearly converges. Here we go. One more. This time the integral from 0 to pi over 2 of tan x dx. This is a little more subtle here because the upper bound pi over 2 actually makes the cosine, the denominator of the sine over cosine, the tangent function, it makes the denominator 0. So 1 over 0 dne, undefined, function not continuous, it's improper at pi over 2. So we replace pi over 2 with w, and we take the limit as w approaches pi over 2 from the left. So another substitution situation. Tan x is sine over cos. We'll replace you with cos. Du is minus sine. Put that back in here. You end up with minus the integral of 1 over u. We've done this one a couple of times. And that's just minus ln u, or if you want, minus ln of cos x. Once again, I forego the plus c since we're going back to a definite integral right now. So we have the limit as w approaches pi over 2 from the left of the answer to the integral between w and 0. Plug in upper bound, plug in lower bound, cosine of pi over 2. Cosine of pi over 2 is 0, we just saw that. And the ln of 0 is negative infinity, so that's minus infinity. And since ln 1 is 0, we end up with infinity, and this integral will diverge. One more example, example 5. This time 0 to e of ln x. Why is this improper? Because if I put in the 0 into the ln x, I'm going to get ln of 0, which is minus infinity, does not exist, yada yada yada, we know the song. So we replace the 0 with the w, we take the limit as w approaches 0 from the right side, and this time it's not a sub, it's a by parts, right, with the ln x thing. So u is ln x, du is 1 over x, dv is dx, and v is x. uv minus the integral of v du shall give me x ln x minus the integral of x times 1 over x, which simplifies to give you just 1. and the integral of 1 is just x. I take out the x for the sake of simplicity, still forego my plus c because I'm going back to a definite integral in a moment. So here we go, back to the limit with the bounds. W goes to 0 plus, bounds up e, down w, plug in your e, plug in your w. Nothing happens much in here because ln of e is 1 and 1 minus 1 is 0. But the second half is most interesting. Why is that? Well, a bit of unexpected problem, because as we replace infinity with 0, we get 0 times the ln of 0 minus 1, and the ln of 0 is minus infinity. So that's really 0 times infinity, and that means that it's not undefined, it's actually undetermined. Now, undetermined means that, well, we don't really know what the answer is. So it's actually worse than perhaps other indetermination because we can't use L'Hopital. L'Hopital, if you remember, is good only for 0 over 0 or infinity over infinity. So before we can do anything, we must transform the expression. So the limit as w goes to 0 plus of w times ln of w minus 1. I'm going to take that w here. I'm going to bring it down as 1 over w, which will have the effect of course, leaving the numerator as it was, but the denominator now becomes 1 over 0, which is infinity. And we recognize minus infinity over infinity as a hospitalizable form, so we are applying L'Hopital. So the limit as x approaches 0 plus of this new function, we derive the top, we derive the bottom. The derivative of ln w minus 1 is 1 over w, and the derivative of 1 over w, which is really w to the minus 1, is minus 1 times w to the minus 2, but I can bring it down as w squared. I can flip my fractions and simplify. I am simply going to get minus w, and upon the replacement of w with 0, I get that the second half of this limit is 0. So if we actually bring back what we had at the beginning, the first half was e. Now we know that the second half is 0, and e minus 0 is just e, so that the integral converges. I will leave you with a couple of good-to-know little expressions in this chapter, some useful things that we are going to bump into. E to the infinity is infinity. E to the 0 is 1. E to the minus infinity is 1 over e to the infinity. And in e to the infinity, we just saw is infinity, so that is 0. Ln of 0, minus infinity. Ln of 1, 0. Ln of infinity is infinity. And on this note, I bid you farewell. I will see you in the next improper integral problem.